Bismillahirrahmanirrahim. Today, inshallah, we shall talk about angles of polygons. Now, polygons, if you recall, were two-dimensional geometric figures that had straight sides and they were closed, and they had interiors and exteriors, etc. So here's an example of a polygon. And this polygon is five-sided. Here's one side, two-side, three-side, four-side, five-sided. And a five-sided polygon is called a pentagon. So this is a five-sided polygon or pentagon. Now all the sides here are of different lengths, seems to me, and if they were all the same length, then it would be called a regular polygon, a regular pentagon. A regular polygon is the one that has all the sides are congruent and all the interior angles are congruent. Now, if you recall, the interior angles are angles that are on the inside of the polygon. As I said, a polygon has an interior, that's this, and it has an exterior, that's this. So the inside of a polygon is called the interior, and naturally, and the outside of the polygon is called the exterior. In the same way, a polygon has interior angles and exterior angles. So if you were to, let's just label this polygon as A, B, C, D, E. So we could call this polygon just by tracing the vertices. So it's a pentagon whose name is A, B, C, D, E. So here's a pentagon. It's a non-regular pentagon whose name is A, B, C, D, E. So this pentagon has angle A, angle B, angle C, angle D, and angle E. Those are all interior angles. They're not necessarily the same. It's like this, and then like I'm giving them different symbols. So those are all interior angles. So let's just say label one of them or so. So this is the interior angle. And then their exterior angle, right? So these are all interior angles here, like this, A, B, C, D, E, and then their exterior angles. Now you have to be careful when you're defining these exterior angles. Now the exterior angle is the angle that's supplementary to the particular interior angle you're talking about. For example, if you're talking about this angle A, right? Now if you were to extend this particular side, if you make this like this side a little longer like this, the angle that is on the outside there, supplementary to this, would be the exterior angle. Okay, now you could say, well, we extended this side here, how about we extend the other side? Well, that's another exterior angle. Let's say if we were to extend this side over here, that would be the exterior angle that's also on that vertex. Now however, there's two exterior angles for every interior angle here, you know what I'm saying? Because if you extend this way, extend that way, but these exterior angles are they're vertical angles, so they're congruent. So it doesn't matter which side you extend. So for example, here you could extend this side like this and get this exterior angle, or extend this side like this and get this exterior angle, but those are vertical angles and they're congruent. So it doesn't really matter which side you extend to get the exterior angle, because they're both going to be the same, they're going to be congruent. Okay, so nevertheless, every interior angle has like a best buddy, and that's the exterior angle. So this is the interior angle, okay, and the exterior angle that goes along with it, you would get that by extending or extrapolating this line over here like this, or from the other side you could extrapolate or stretch out that side. Now, it doesn't matter which side but if you want to find all the exterior angles, you kind of have to be consistent, right? So you're not confused. So every interior angle has a exterior best buddy. So if you're the way you can do that is you either go like clockwise or you can go counterclockwise and find all the exterior angles. So in this case, let's go clockwise like this. So okay, so if you're going to go clockwise, the exterior angle that goes with E, you would extend, that's this side, and that would be the exterior angle right here. And going again this way, clockwise, you extend this angle right here, there's the exterior angle that goes with D. And if you were to extend this side here again, extending this side like this, you would get this particular exterior angle like this over there. And if you were to extend this side over here, you would get that particular exterior angle. So that's how you get exterior angles. So every interior angle has a supplementary angle, so to speak, that goes with it. It's best buddy, and that's the exterior angles. So polygons have interior angles and they have exterior angles. Okay, so polygons have interior angles and they have exterior angles like that. Okay, so that's the first thing that you have to understand. Now, as I suggested, to get the exterior angle of the corresponding vertex, you just take either extend this side and just make the line longer, or you extend this side, make that side longer, and you get the exterior angles. And there are two, like this over here, but they're going to be congruent because they're vertical angles. So it doesn't matter, except to be consistent. This time we went clockwise. You can also go counterclockwise. So if you're going this way, you extend this way, extend this way, you extend that way, you extend that way, so you're not getting too many exterior angles, so you're not confused. Okay, that's easy enough. So we have interior and exterior angles. The second thing we have to appreciate is that polygons have diagonals. The diagonals are segments that connect the vertices of the polygon. So if I were to take from here B and connect it to D over here, that would be a diagonal. So diagonal is a segment that connects two vertices. Now, from B you can connect to D, from B you can connect to E over here as well. There's no point connecting B to A because that's actually just one of the sides of the polygons, or B to C, that's all because one of the sides. So diagonal is basically a segment that connects non-adjacent vertices. That's because C and A would be adjacent neighbor vertices, because you can't really connect neighbor vertices, because you connect them, you get like the side of the polygon. There's no point, there's no it's not a diagonal, there's just a side. So diagonals are segments that connect vertices, non-adjacent vertices. Now, you can connect B to D, and they're diagonals from every vertex, actually. So you can A here, go like this, and you can start with E. Here we go. You can start with E, but then from E to B is the same as B to E. We got that one already. That one's already done. So that would be it. So it's kind of like that, right? So every vertex, you can generate diagonals starting at every vertex. All right, so that's easy enough to understand, I think, inshallah. Okay, now let's say I wanted to find the sum of all the interior angles. So what we're going to try to do today is to find the sum of all the interior angles of polygons. That's one of the things I'd like to do today. For example, if you were to add up measure of angle A, and then if you were to add up to measure of angle B, and if you were to add up to measure of angle C, and then the measure of angle D, and the measure of angle E, what would the sum of all of these angles would be? If you add this, whatever those angles are, I don't know, let's make a guess as to what this could be. Maybe this is like 130 degrees, I'm just guessing, and this is like 110 degrees, and this looks like 80 degrees, and this looks like that's a pretty big 135 or whatever. So if I were to add up all of these angles, what would be the sum of them would be? Now, I don't know what these angles are, but if I were to do that, what would be the sum? So it's clearly not going to be 180 degrees, which is like the sum of interior angles of triangle, right? Because already here I have more than 180 degrees, it looks like over here. So how do we go about finding the sum of the interior angles? So here's our first goal. We want to find the sum of the interior angles of a polygon. Okay, so that's our goal. So what is the sum of the interior angles of a polygon? To do that, consider the following. So I have here 4 different polygons. Okay, so here's, of course, is our good friend, the triangle. So this is a triangle, and this is a 4-sided polygon. This is a quadrilateral, and this is a 5-sided polygon, which is a pentagon, and this is a 6-sided polygon, and that's a hexagon. Okay, so what I want is the sum of all the interior angles. So in this case, I want the sum of this, this, and this. And in the case of the quadrilateral, I want the sum of all of these 4 interior angles. And in the sum of the pentagon, as I said, I want the sum of all of these interior angles. And the hexagon, I want the sum of all the interior angles. Well, as I see that in this picture, it's not going to be 180 degrees like the triangle, because already this looks like a pretty big angle, and these are two obtuse angles. And if you add up two obtuse angles, obviously it's going to be bigger than 180 degrees. And okay, so it's not going to be 180. So how is it going to be? Well, consider the following. Okay, let's say if you have this triangle over here, okay, and the sum of the interior angles of a triangle like that plus all those three, that's 180 degrees. We know that from before. So the sum of the interior angles of a triangle is 180 degrees. Okay, now I have a quadrilateral here. Now if I do this, watch, I'm going out of a quadrilateral, I'm going to connect the two vertices here. That is, I'm going to make a diagonal out of this. So I've drawn a diagonal. Now what I see here are two triangles, right? Well, what I do know is this plus this plus this, those three angles, that's 180 degrees, isn't it? Because that's a small triangle over there. And then I have this over here plus this over here, and then I have this over here, and those three angles add up to 180 degrees, don't they? So for these two triangles that I have over here, each of them have 180 degree sum. So this angle plus this angle plus this angle, that's 180 degrees, and then this angle plus this angle plus this angle, that's 180 degrees. Now look at this. This is one angle of the quadrilateral, that's another angle of the quadrilateral, that's another angle of the quadrilateral, and that's another angle of the quadrilateral. In other words, if I were to add up all of these angles up, I get the sum of the interior angles of this quadrilateral. So it's going to be 2 times 180 degrees. So that's 180 degrees over here. That's going to be 2 times 180 degrees. Okay, that's I see something there. How about a pentagon? A pentagon, if I were to draw this out, let's do this again. Now I use one vertex. You can use any vertex to draw these diagonals. You get the same thing. It's just like the idea is to divide up the polygons into triangles, and you can see you can always divide up polygons into triangles, right? Because all the sides are, you can always do that. So now I have three triangles, right? And then you get the idea here, right? Because now you can do the same thing. Here's this angle, and that 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 angle. These are not congruent, of course. I'm just marking them like that. So again, you can see if you add up all of these angles, and those are all the angles of the triangles. So if you sum up all of the angles, that's going to be 3 times 180 degrees, isn't it? So it's going to be 3 times 180 degrees like this. Oh, I see a pattern there. Okay, so, how about this? So I do this. This is a hexagon. It's a funky looking diagonal there, but there you get the idea, right? So, here we go. So this is a hexagon. So how many triangles do I have? 1, 2, 3, 4. That's 4 triangles. 4 times 180 degrees. So I'm getting a pattern over here, right? So when I have a quadrilateral that is 4-sided, right? The sum is 2 times that. When I have a pentagon, the sum is 3 times that. When I have a hexagon, the sum is 6 times. When I have a hexagon, it's 6-sided. The sum is 4 times that. And that kind of makes sense because you see, for any polygon, how many triangles can you make out of it? Well, if it's a 7-sided polygon, you can make 5 triangles out of it. If you have a 20-sided polygon, you can make 18. The reason is because you can't use these two sides when you're making triangles because you can't make a diagonal out of it. You can only do diagonals to non-adjacent vertices. Well, how many non-adjacent vertices are there? There's 2 non-adjacent vertices. So the number of triangles that you can make out of a polygon is going to be always 2 less than the number of sides. That's pretty cool, right? Because then you can get like a formula, because then you can say the sum of the interior angles is going to be however many sides there are, and is the number of sides of a polygon, and you take away 2, right? You take away 2 from that, times 180 degrees. There it is. So the sum of the interior angles, of a polygon is going to be 180 degrees times 2 less than the sides. Okay, so n is the number of sides. N is the number of sides. So number of sides of polygon. So if you have a 50-sided polygon, okay, you can make 48 triangles out of that. 48 triangles. The reason is because they're two adjacent vertices, and you can't make triangles out of them, and then you can make triangles with the rest of the vertices. Okay, so the sum of the interior angle of this 50-sided polygon is going to be 50 minus 2 times 180 degrees. Ta-da! There we have it. Okay, so this is very fascinating, interesting. The sum of the interior angles of a polygon is going to be n minus 2 times 180 degrees. So the measure of angle A plus B plus C plus D plus E, that's 5-sided. That's 5-sided. So, and you can make 3 triangles out of it, times 180 degrees. Okay, that's 3 times 180 degrees. That's 180, 360, and that is going to be 540 degrees, like that. Wow, that's kind of pretty cool. Okay, so here is a summary of what we talked about. The sum of the interior angles in a polygon. If you have a quadrilateral, you can divide that into 2, like we did over here. You can divide the quadrilateral into 2. So a triangle, of course, has 3 sides, and it's going to be 180 degrees. A quadrilateral has 4 sides, and you can divide into 2. If you have a pentagon here, you can divide a pentagon into 3. So 5 sides, 3 triangles. 4 sides, that's a quadrilateral. You can make 2 triangles. Of course, 1 triangle here. And if you have 6 sides, then you can make 4 triangles out of that. Okay, so because here we go, that's 1, and that's 2, and you draw that out, and then you can see you can make 4 triangles because there are 2 adjacent vertices. As these over here, you can't make triangles, but you can make triangles of the rest of the vertices, right? So that's how you do it. So we can say that for like octagon, which is 8-sided. So let's just go through this. Triangle, quadrilateral, pentagon, hexagon, 6-sided, heptagon. Heptagon is a 7-sided. 7-sided polygon, you can make 5 triangles out of it, and that's going to be 5 times 180 degrees. Octagon, which is 8-sided polygon, you can make 6 triangles out of it. It's going to be 6 times 180 degrees. And for a n-gon, which means n sides, you can make n minus 2, 2 less than the number of sides. Therefore, the sum of the interior angles is going to be n minus 2 times 180 degrees. So you can that's the formula for the interior of the sum of interior angles of a polygon, like that. All right, so that's easy enough. So that's one way of understanding this problem. The sum of the interior angles is the number of sides minus 2 times 180 degrees. So that's the sum of interior angles, like that. Okay, that's fascinating. I think that's kind of very cool. Now, there's another way of finding the sum of the interior angles of a polygon. And I kind of used to this one because this might have been the first way I learned. So if you have, let's say, 5-sided polygons here, what you can do is just in your imagination, you can just draw a point in the center of the polygon. It doesn't really matter where. And what you do then is you make triangles like this, starting from that one center, like that. Okay? So, and if you do that, you will see that if you have a pentagon, this is a 5-sided polygon, right? If you 5-sided polygon, if you do it like this, then you can make 5 triangles. It's 1, 2, 3, 4, 5 triangles, right? So from this version, if you were to start from like a vertex, you can make 3 triangles. But if you start from the center over here, and you can make as many triangles as there are sides. So if you start from the center, you can make 5 triangles like this. Now, if you add up all of the angles, if you were to add up, for example, this one, 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 and right? So then you would get all the interior angles. But look what happens. If you add up all, if you said this is 180 degrees and this is 180 degrees, all of these are 180 degrees. So if you were to add all of them up, you would be adding up all of these angles here, but you will be also adding up these angles over here. You would be adding this one, you'd 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 be adding this one. So if you do 180 degrees times 5, okay, you would be adding all of the interior angles, plus you'd be getting extra angles that are actually not there because you invented them, because that's in the center of this polygon, right? But then you'll notice that all of these angles add up to 360 degrees because, you know, it's like a circle. So if you were to make 5 triangles starting from the middle over here, so you have 180 degrees like this, 5 of them, if you do 5 times 180, you have to subtract the 360 degrees, and this will also give you the sum of the interior angles of a polygon. Okay? So you can do the same thing with, for example, a quadrilateral. If you have a quadrilateral over here, it's 4-sided, right? And you can imagine like a point somewhere over here, and then you can construct a quadrilateral. You have 4 triangles over here like this. So you have 1, 2, 3. Because there are 4 sides, you can make 4 triangles. That's 180 degrees times 4. But then you have to subtract again this interior, those angles in the middle, right? And those angles in the middle, they add up to 360, because like, whoa, like one big circle, so minus 360 degrees. So that's another way you can find the sum of the interior angles of a polygon. So there are 2 ways of finding the sum of interior angles of a polygon. So this is sum of the interior angles of a polygon theorem. The sum of the interior angles of a n-sided, n number of polygons, of a convex polygon. We shall elaborate on this inshallah next time. Convex means it's not dented, if you remember. Those are concave polygons. So this only applies to convex polygon, which is a little detail we shall add in the future inshallah. The sum of the interior angles of an n-sided polygon is n minus 2 times 180 degrees. That's like over here, because for any n side you can make n minus 2 triangles in size. So each of these triangles is 180 degrees like this. And because the sum of all the angles of those is the sum of the interior angles of a polygon. So you can do it n minus 2 times 180 degrees, or you can make a point in the center and draw triangles, and you will draw 5 triangles if it's a pentagon, and 6 triangles if it's a hexagon. So it's going to be n times 180 degrees, but then you have to subtract this 360 degrees. So the sum of the interior angles of an n-sided polygon is either n minus 2 times 180 degrees or n times 180 degrees minus 360 degrees. I don't memorize these formulas. I'm able to generate these formulas, and that's why I encourage you to do, because if you understand the concept, you really don't have to memorize the formulas. And I think this is actually quite a beautiful concept, on which we shall elaborate next time. Until then, الصلاة والسلام على رسول الله والحمد لله رب العالمين. السلام عليكم.